metal 3D printing. We're very excited to learn a lot more. I'm Mike with 3DNA Dental, and Paul here organizing this webinar.
Hello, everybody.
Yeah, we're going to go ahead and have Nate and George introduce themselves and give us a little introduction to Mastrex to begin with, and we'll go deeper and deeper as we go through all this. So please, I think Nate, maybe if you want to give it a start.
Yeah, no, sounds great, and certainly thanks for having us. But first of all, Nate Harris, I'm Vice President of Sales for North America for Mastrex. I've got well over a decade of experience in additive, leading organizations, growing startups and scale-ups, and came to the team fairly recently. I'm pretty excited about what Mastrex has in terms of technology, and pretty excited about the level of interest we've had in the dental space. So enough about me. George, quick intro.
Yeah, hi everyone. I'm George Cisneros. I'm a pre-sales and application engineer with Mastrex. Got a background in mechanical engineering and laser powder bed fusion. I've spent the last several years helping customers develop metal printing processes and bring additive manufacturing into production in-house. And so yeah, I'm excited to share with everyone today about this technology, our company, and the possibilities that it can bring.
Oh, very exciting. Yeah, I don't know if you guys want to go and follow most of your presentation, and we'll pop in with questions. I'm happy to do it that route. Otherwise, I can bombard you with questions left and right if you guys, whatever works.
Yeah, sounds good. I'll maybe just a quick thanks, and then maybe educate our audience a little bit about Mastrex in case it's a new logo you're seeing in the field. But first of all, again, thanks for having us today. We're certainly excited to be part of this conversation because dental manufacturing, I think, is in a really interesting sort of phase right now. Labs are under a lot of pressure to move faster, control their costs, obviously maintaining quality, and still keep up with a lot of complex clinical demands. And at Mastrex, our focus has really been pretty simple. We make industrial metal additive manufacturing a little more accessible than what it has been in the past. And it's not watered down. It's not a hobby level kind of technology, but it is true laser powder bed fusion technology that dental labs and manufacturers can realistically bring in-house. So today, again, I think this is the intent of the discussion, is I wanted to feel less like a formal product pitch and a little bit more like a practical discussion where, where does metal 3D printing fit, and what problems does it solve, and how can a lab should think about whether this technology makes some sense for them. So want to know a little bit more about Mastrex, or where do you want to start?
Yes, let's learn more and more about Mastrex. And I'll say, if you want to, I don't know, your background with, you talked about Stratasys and photopolymer and how all of this sort of like grew together, and it's a big industry. So you're welcome to bring all that in as well. So.
Yeah, no, sounds great. And for those that weren't on before we just started the recording, I was just sharing with Mike that I'm very familiar with the Lux Creos and Haygears, and certainly the adoption of additive in the dental industry in general, which I think is great, because I think that's really set a precedent, a positive precedent, that the additive plays a role in this particular vertical space. But anyway, back to Mastrex real quick. So our company is built on more than 12 years of industrial manufacturing experience. The company's background includes polymer 3D printing, but also fiber laser cutting, CNC equipment, and automated production systems. And I think that history matters because laser powder bed fusion, which, quick quiz, has been around since the 80s and 90s, isn't just about putting a laser in a box. It's about motion control. It's about optics. It's about thermal management, powder handling software, a lot of other different things that are part of that entire process. And so our mission has really been to bring this industrial grade laser powder bed fusion technology into reach for a lot more organizations, including dental labs, that may have looked at powder printing before and thought, way too expensive, too complex, or it's too far away from what we do every day. So with that, we have a quick slide here. We've got 3 broad platforms, from desktop to production systems, to develop maximum density parts with feature accuracy you can really only get with laser powder bed fusion, which is very important in the dental industry given the fine features and applications necessary. And for those that may not know, laser powder bed fusion is a process where a thin layer of metal powder is spread across the build platform. High power laser selectively melts the geometry of the part and then another layer of powder is applied above that. And that process continues to repeat layer by layer until you get a fully dense metal component. So some people are aware of that, and there's different methodologies for metal printing, but just wanted to clarify what that is for us. And so for dental, the practical benefits are pretty clear. You can produce very complex geometries directly from CAD. You reduce material waste compared to like traditional milling. You can nest multiple parts in a build, and you can move from digital design to metal part without all the traditional casting workflow. And I think the important thing is laser powder bed in particular creates fully dense metal parts, usually 99.5 to 99.9% density range. So this is not a fragile or temporary output. It's a production metal component. And then
Real quick,
slide
if you
4.
don't mind,
Yeah, go
I
ahead.
want to jump in a couple questions. So on the back, if you go back one there, the density that you're talking about, does it happen off the printer or after annealing?
Yep, that is directly off the printer. Yep.
Off the printer,
And
wow.
typically it is that 99.9%. We drop it down to that 0.5 because that's all some people need in the dentistry, and most parameters we use are always that maximum density, which is really nice because compared to traditional methods such as a raw material that you're milling or even casting, there's more pores and inclusion, meaning there's slightly less mechanical property. So,
Which is amazing. I don't think that, like in the past at least, metal 3D printing has had the reputation of not making extremely strong things, and I think that's been a misnomer for a long time. So
Yeah.
I wanted to focus on that a little bit. And the other thing I wanted to ask about this is when we say 25 microns for small features and 50 for larger parts, first of all, why is there a differentiation in the accuracy between a small and a large part? And then the other thing is, in dental specifically, we're very interested in, for example, like bases or tie rods, where it's like, if we're 3D printing actual implant aspects, or do we still need to have a milling step to get it accurate enough for our screw position? Because I know in the past we have had to have combinations of metal 3D printing to a CNC in order to have that like exact measurement. So if you can get into that a little bit.
yeah, sure. Yeah, this is one that I can answer really well. First part of that question, why the difference between small features and large features? Typically, that has to do with the laser that you're using or the machine that you're using. So for smaller features, we're typically using our smaller printers, the MX 100, MX 120, which has a little bit smaller beam diameter. And that's responsible for that higher tolerances, or the 25 microns. With 50 microns larger parts, you're typically going to be printing that on our larger systems, which we're not necessarily featuring here because we have the 150, 220, 300, 400, even all the way up to like a 800, which will be available soon. So those are very, very large parts on the order of, feet or hundreds of millimeters. And so that's still really impressive accuracy across that large distance. It's a slightly bigger beam diameter just because it would take forever if you use the really small ones. However, for dental, you're typically talking about small like tooth size parts or something, and so you want the fine details and you want the smaller laser.
Absolutely. And then so with like if we're doing all in X and we're making bases for all in X, like tie bases and things like that, or not tie bases, but blanking on the name right now, but basically anything that we have to put screws through and have it match into an implant, like how accurate is it at this point
Yep. So I can say as far as 3D printed threads go, we have gotten to a place where we've gotten the process and the parameters down that you can make fully functional 3D printed threads. But typically you would print the majority of the thread and then chase it with a thread die and tap to make it fully accurate. But that
in that case, we're more talking about like making a hole inside of our part where our implant's going to sit, and then the screw's going to go through it. So it's not even like that it's threaded, you know what I mean? It just is like a perfect shape to fit over the abutment that's on the implant. And then there's a screw that goes through your part into the abutment. So the real question is that, this is been around for a while. So the real question is like most of the part that I know of, we have to go from the metal 3D printer and then do a little bit of a CNC step in order to get it, good enough. But at 25 microns, I'd be surprised if you really need to do that. But it just depends on like,
Yeah,
we're going to get into it, right? Where it's like the powder size itself and the uniformity of the particles matters a lot and all that kind of stuff, right?
Yeah. Yeah, I would say that or that tolerance is really repeatable, really accurate, and as long as your surface finish is acceptable for you, then yes, we can dial things in and we can hold that straight out of the printer. There's no need for like a CNC type machining. If it was like you needed a very fine surface finish, a polish or something, then maybe some sort of small amount of post-processing machining might be necessary afterwards. But
sure,
no, that's where I would say makes the huge difference. It's just down to the surface tolerance, but those tolerances are very repeatable, very accurate.
Awesome. That's going to be a big one for the labs, is to know, what that process looks like. So, and then I guess as we get further, we'll probably talk through like what the post-processing steps are and how much that might mess with, if we're
sure. Yep. We'll get into that here. Yep, a little bit.
Awesome.
Down.
Sorry, I know I jumped down on that, but I figured it was.
That's what this is for. That's perfect.
Exactly. Yeah.
Yeah. I was just going to make one more comment, and then we'll continue on with some other stuff too about maybe where metal is in 3D printing in the dental space. But I was just going to make a comment for those that live in California, or at least minimum like to visit California. All our printers are manufactured and assembled in San Diego, or San Diego if you're a Ron Burgundy fan, but it's all our components are all assembled from either the U.S. or Western countries. So that's something I think some people tend to find is important. So all the supports here, it's all manufactured here, distributed from the U.S.
Awesome, that's huge. I don't know that anyone else is doing that. Do you know if anyone else is doing that? Yeah,
I don't. Not familiar. There might be one other small company out there, but yeah, the majority of them are you're foreign, European based, something like that.
You guys are ahead of the game on that then, right? I feel like that's important right now more than ever.
Yeah.
Yep. Keep it domestic.
Beautiful. And I think just my comment on this is like, of all the printers in the metal space that I've seen, especially trying to move towards desktop, you guys have a very sleek, good looking printer, I would say.
Thank you.
And yeah, I don't know if we can get into like one of the things that I saw happening slowly was just the change from these huge printers and the more expensive footprint version of this where we're at now. And I feel like one of the bigger concerns, especially printing titanium, was grounding and how you're working with the filter. So I'd be interested. I don't know if we're there yet. It'd be really, I don't know. I obviously took a look at your presentation, but I don't know that we get into those details later. So feel free to push off any of these questions to later if it's in the presentation. But how do you handle the filtering aspect especially for titanium with that smaller footprint printer?
Yeah, George, you want to hammer that when we get to the slide on materials?
Yeah, sure. Yeah, we can.
Yeah, so we've got a slide queued up because I know you mentioned materials was going to be an important topic. Cobalt-Chrome versus titanium and some of these other materials as well. So we'll nail that. I'll just say one more thing, and then we can spend a little more time, I would say, on the technical side. But I think that it's interesting. I said earlier about the idea of 3D printing metal in dentistry, and I think it's really moved from being, I think, like an interesting future technology to something that's more practical production tool now. So for years, dental labs have had to choose between traditional casting, milling, outsourcing metal work. Each of those can absolutely work, but there's also comes with some challenges with lead time, labor, material waste, inconsistent turnaround, pressure on margins, all those sort of things that we know and love, right? And I think what's changed now is powder bed fusion has matured, the machines are more accessible, the materials are better understood, which kind of goes to your comments earlier about how we can have such dense parts, right? All that's kind of coming together. And the workflows are being more standardized. So labs are getting more comfortable working in a digital environment. I mean, there are days where we used to get impressions. Now I can go in there and just get my tooth scanned. And so CAD design, nesting, things like that are not entirely unfamiliar to a lot of labs these days. So the next step was really bringing metal into that same digital workflow. And for a dental lab, more control over quality, control over delivery, control over cost, control over the customer experience. Instead of waiting days or weeks for outsourced metal parts, they can sometimes think about same day or next day. And I think that's what's kind of the exciting part about metal into the dental space is this is not about just adopting a new machine. It's about giving labs just a way to become more competitive, more responsive, more profitable, while producing strong price, fully dense metal restorations in many cases. So I think it's a good time. I mean, it solves a lot of problems.
Yeah, it's a incredible technology that it's like all these things fitting together, and like you said, once you go fully digital, it's not only it's like what you can imagine to physically having it in your hands in a day or 2 days. It's just such a cool feeling.
Yeah, for sure.
Here we are.
Yeah, so through this off here, because I think there was a question at one point someone was asking, why metal 3D printing and what problems does it solve? And I think this is, and by the way, if this is a bit of an eye chart and people have a hard time seeing it, this is being recorded. It'll be distributed, so you'll be able to pause on this and squint. But I think this is where the conversation becomes a little more practical for dental labs. Traditional casting milling, they've served the industry for a long time, but they come with limitations, as I mentioned before. Wax up, investing, burnout, casting, a lot of hand finishing. Each step kind of introduces time, labor, potential sort of variability. And milling is useful, but it can be certainly wasteful when it comes to metal material, limited tool access, geometries, etc. So with powder bed, you're building directly from a digital file, which means fewer manual steps, less cumulative error, better material efficiency, and then the ability to produce many parts in one build. So I just say, just as a final thought, just a few key points on this slide is first, lead time. If you're outsourcing metal work today, you're often waiting for someone else's schedule. Bringing it in-house gives the lab more control. Second is quality consistency. When the workflow is digital and repeatable, you reduce the variables that come from multiple steps. Third is margin. Obviously, if you're outsourcing today, meaningful amount of metal work, that margin is leaving the building. So in-house production lets you capture more of that. And I'd say the last comment is capability. So metal 3D printing can produce geometries that are very difficult and sometimes inefficient or impossible with conventional methods. So very often people start with one project that they're already outsourcing, one project where they know they can make a buck, and then the next thing they know, they're using metal printing for a whole bunch of different applications. I'm sure you've probably experienced that with a lot of the polymer users that have been using their Lex Creo, their Hay Gears, their standard printers today. They find all kinds of projects they can make a buck with.
Yeah, sometimes it's a problem because it's hard to know what to focus on, right? So you gotta prioritize. But yeah, no, it's incredible. The same technology can do so many things. So.
Yeah. And usually there's always, the president or the CEO comes into the lab at some point and has you start building projects for his son or his daughter's middle school project or something. But yeah, point being is you find ways to eat up the capacity on the machine and use it for a number of different things.
Definitely. That's great. And yeah, like you said, the geometries that you can only print, and the idea of printing, even things that less dental related, but in the industrial space, printing things that have moving parts within themselves, and sealed compressors, things like this that we've never been able to even conceive of, and now here we are. So
that's
very
right.
exciting times.
That's right.
Oh, here we are. So this is the X100. And I don't know, go ahead and do your thing, but I think talking about the 300 watt, the fact that you guys have that in there, and that's like more than enough and should last us a long time, I would think.
George will walk us through some of the text on this, but I would just comment that we were just at a show in Anaheim not too long ago. Sounds like I'm pimping California right now, but anyway, I was out in Anaheim for a show out there, and we had the MX100 on display, and people were blown away. We actually even had a part printed out on the MX100, sitting right next to a part that we outsourced on a $500,000 powder bed fusion printer. And we were trying to get people to see what's the difference. Can you tell the difference? And no one could tell the difference. And so it is a quality system at an entry-level price point that people have just not yet seen to this point. So it's affordable by design. But anyway, taking away from George's time, talk to us a little bit.
So now that we've learned a little bit about Mastrex, I think it's important to learn about our printers and our portfolio and what we're offering here. So the first one we're showing is this MX100, which we call an entry level or a desktop printer, and it truly is a desktop metal printer. It's got a footprint of about maybe 2 feet by 2 feet or 1.5 by 2 feet. And it's about 2 feet tall or 3 feet tall. So it fits on a table, which, previously there were no machines of this size or capability. It required a little bit bigger footprint, which meant that it required a bigger lab. And so just some of the features to run through here, you can see it has a build volume of 100 millimeter diameter with an 80 millimeter build height, which is capable for handling most dental applications. So that's one of the reasons why it's really focused towards that. 300 watt laser, more than enough power for handling all the industry standard materials. We will get into the materials that are commonly used in dentistry and why we would use them here in just a little bit. I guess a little bit more about it. It's got a laser beam diameter, starts at about 35 and go up to 60 if you need faster production. And then one of the really nice key features about this is the power requirement. It actually runs on 120 volt, which is just standard wall power that you can get anywhere. So it doesn't require any real special laboratory or setup. It can be integrated in your existing workspace already. So it's a very, very nice feature. And you can see we've got a starting price of about $39,000. Same thing, you won't see basically anyone else in the industry who will advertise their price. And that includes delivery, setup, training, and 2-year warranty on top of that. So that's a little bit about the MX100. I think we could probably move on to our next machine offer here, the MX120. So this is another great entry-level machine. It's a little bit bigger build volume, 120 millimeter diameter, 100 millimeter build height. So you can fit some more parts per build, which can help with the economics of the build. It uses that same 300 watt laser, has about the same layer height capability, 20 to 50 microns, and all the same materials are available. And then same thing, it runs on 120 volt. So again, it does not require any special voltage power setup. So this is both a great way to get started if you know you've got a large queue and a lot of orders. You can get a little bit more throughput with this. It's about in the same ballpark as far as price goes. It's not too big of a step up. And so that's the advantage there. And then I would say our next machine, which is really good, better for more like serial production. You start to get into our first square build plates. So this one is the MX150. And so it has a build volume of 150 millimeters by 150 millimeters by 120 millimeter build height. So it's a little bit bigger, and with it being square, that means you can, again, nest more parts on the build plate, which can help with throughput. And then as far as laser power goes, that starts with a 500 watt laser. So a little bit bigger laser beam and a little bit more laser power, but that allows for faster production, a little bit faster lasering of the parts.
That's a single laser, or is that 2 lasers?
Yes, that is also a single laser. Yep. And then you can see the laser beam diameter is slightly larger, starts at 50 microns. Overall, that won't have much effect of your tolerances or of the part. And one final thing to note for this one, it has listed voltage of 380, and that's triple phase. So that's industrial voltage, and it can actually run anywhere from 208 to 480. And that's something that we would set up during the time of ordering. So it requires a little bit more infrastructure. However, as far as footprint goes, you can see again, it's that we've got it listed there in inches. It's about 3 feet by 2 foot footprint, and it's a full height machine, so it's not going to sit on a table, but you can exit. So it's still overall very, very small footprint for the build size that you are getting.
So just to clarify, somebody that has regular power, like regular two, let's call it single phase, or whatever. So it's like 208, 220. Can they run this machine, or do they need to get industrial like 3-phase power?
Industrial 3-phase power would be ideal. You can run it on the single phase. It would have to be converted. You can get a like a rotary converter from single phase to triple phase, and then you could also get a transformer if need be to move it to the correct voltage.
Okay.
So it is doable. That's something that we've looked at and can be done. It just depends on what makes most sense and what your infrastructure looks like.
Sure.
So that's the reason why we've got various things, why we call this one a little bit more production. Those the little bit smaller systems being on 120 volt, it's easier to set up with a lot of people's existing labs and infrastructure. But if you did have a lab that had triple phase, then this would be a fantastic way to either begin or increase your throughput if necessary.
Sure.
And just to sort of reinforce what George was talking about too, Mike, in terms of size, you know, if people are just wondering how big is this thing, it's hard to tell from the picture. Think of it as probably about the same size as the fridge that you have in your garage to keep your boat sodas. So that's probably about the size of the system itself. Now we'll talk a few minutes too here about what's some of the ancillary equipment that needs to come along with this. But as you mentioned before, those price points we're sharing include the system itself, the 2-year warranty, install, training, integration. So you're out of the gate with that, and then, you know, depending what labs already have or what labs might need, there's some ancillary pieces you might need as well.
Yeah, and actually, I was going to go into just a little bit more detail too, because you had, or you can go back to the machines. You had asked a little bit about the filter and stuff. So I can say with these smaller machines, the MX 100 and the 120, everything is basically built into those machines. The lasers are air cooled. We have built-in powder handling and filter also. And it's the same thing with the MX 150. Everything is built in, the filter. The only difference is with the 500 watt laser, you do need an external chiller that is included in the price too. That can have a little bit more of a footprint. You're talking about 1 foot to 1.5 feet. But it's also something that could be stacked up on top of the machine. So it doesn't necessarily have to actually take up more space. And then we have a couple different filters that are built in. There's kind of like a cartridge filter that is in the smaller machines. So if you think about your traditional, I don't know, like HEPA filter or something on a vacuum, one of the a wet dry vac or something, it's almost like a filter like that in there. And it's got a certain lifespan that it lasts. If you're using it daily, we recommend it. It gets swapped out every 6 months or so. And that's something we would train you to do. It's a simple, easy procedure, but so you would basically remove the old filter, put in a new one, and that's about it. With the 150, it's I believe a little bit more of what we call a permanent filter that's in there. So it lasts about 5 years, and I believe that's using the chalk that's inerting or passivating, and that gets removed and refilled. And that's something that we are also looking at and potentially switching over in our smaller machines too. But that's something that we would work with people and train them up on.
Sure. In terms, and on the smaller one, but even on the big one, when you change from one material to another, does that change how you deal with the filter, or is that a separate, or like the filter is able to work through that material change?
Oh, that's honestly a great question, and that's something that the filter can work through the material change. Yeah, that's not a problem.
I guess I'm from the old days, like especially printing in titanium, there was so much that went into making sure that it was a safe way of doing that. You know what I mean? So I'm just surprised at how, I don't know, it seemingly has gotten well understood enough that it's become less of an issue, obviously. And you know, we get into nitrogen or argon and we talk about how we're doing that, but yeah, the filter part especially I thought was a part of that danger, especially when it came to titanium. But
Yeah,
That's
well, I can say, yeah, no, and you're correct. Like, as someone who's been in the industry for a long time, yes, it is something that used to be more challenging. Yeah, you would want to swap your filter if you were maybe changing materials.
yeah,
You could keep the old one and put it back, like if you were switching back or something, just so
yeah,
you didn't cross contaminate. But with these, the smaller machines, the amount of material that you're going through is it's very little, especially compared to the size of the filter. So that's one issue that helps. And then those permanent filters, as I said, because it's doing a process of essentially passivating. It's the condensate is what it is. So when the laser fires, you evaporate some of the metal into a vapor, and then that gets sucked up, and that's what gets pulled into that filter. And so that can be very, very fine powder, a lot more than the powder or material that you're printing with. So that's what can be a little bit more combustible. Um, but so that is getting passivated with those permanent systems. So then there's really no issue with switching between powder or materials.
nice, perfect. And yeah, I guess it might be covered later, but we're going to be so. Or do we want to talk about the ancillary equipment now before we get into materials?
Yeah, perhaps you could do only before we jump in the materials, let's do ahead of that, because I know when we go to materials, we are going to talk, the difference between titanium and Cobalt-Chrome, some of the others. So George, maybe just give folks an idea, okay, you've talked about the chiller, right? You've talked about, which comes with the system, the 150 in particular. We've talked about the printer itself. But what are some of the other things that people may need to consider? And they may already have some of these things, so they may not need it. But what are some of the things they may have to consider? And what are some of the unique differences between if they are printing in titanium versus maybe the other standard metals?
And
Okay,
and
sure.
real quick, the chiller is a liquid chiller, and it's because you have a liquid cooled for the 500. Is that correct?
That is correct. Yep.
Yes, okay, cool. Sorry.
Yeah, and the 300 watts are air cooled. Yep, no need for a liquid chiller in there. Yep. So yeah, as far as some of the ancillary equipment that you are going to need with this, you need a powder collection system. So that's essentially a vacuum, but one that's designed for sucking up metal powder. So it's usually grounded and something that they would call like explosion proof or something like that. As you can imagine, when you're sucking up metal powder, it can kind of create a little vortex or swirl. So if you don't have the proper vacuum, you could get some potential combustion issues. So we have that. That's included as part of the quote. That can be really useful for removing powder after you're finished printing, or even removing all the powder from the machine if you're doing a material changeover. And then as the benefit, and as we had stated, one of the benefits of this technology is that you can reuse the majority of the material, so you don't have a lot of waste. And so with the powder collection system or the vacuum, you can reuse or collect all that material that wasn't used. And then I would say that leads me into my next ancillary item that you're going to want, and that is a sieving unit. So once you collect all your powder, you need to pass it through a sieve to make sure you remove any oversized particles. You'll get some partially melted particles when you're printing things, and so the sieving unit, you can remove all those and then reuse the majority of your material. And then we have a part cleaning system or chamber. So as I mentioned, after the print, you would vacuum off most of your powder, but there's still a little bit that's going to be left around the part or inside the supports or something like that. And so it's best to have some sort of chamber where you can blast your part or build with air to remove all the final powders. Then a heat treatment oven. So there's going to be retained stress when you print. And so it's best for full mechanical properties that you do it in an oven. And that's one or to relieve the stress and get the full properties out of your part. And that's one area where it differs a little bit for titanium versus Cobalt-Chrome, some of the materials we'd be using. For a heat treatment oven for titanium, you're going to want a vacuum or inerted oven, so you don't get a lot of oxidation on the outside. Gives you better mechanical properties. And then finally, I would say like post-processing equipment, like a polishing equipment or something like that. And that's also something that we offer as part of our packages. And I believe that all of the
Anything about removing the parts off the build tray or the build plate?
yes, yeah. So that's another part. Yeah, removing the parts. So a bandsaw or something to remove those. I mean, they can be removed with a hammer and chisel too, but bandsaw is a good way to also remove
I'm
it.
seeing
And then
people use a what do you call those? A utility. Well, I'm blanking on it, but it's a vibrating tool that
oh, is it say like an air chisel or something like that, or
kind of like that. Yeah, I don't know why I can't think of the name right now, but it's just a oscillating tool that goes back and forth, and it like you can cut it off the build plate as opposed to needing like the full like bandsaw. You know what I mean?
oh, like a sawzall or something like that.
No, I don't know. I can't think of it. It's
I
Like a
mean,
Dremel?
yeah,
Like a
I'll
Dremel
look it
tool?
up so we don't think through it.
yeah.
But the other thing would be then you have to polish the plate, correct? Or the build plate?
So yeah, to reuse the plate, no, you don't have to polish the plate. Just a simple sanding is good enough. So yeah, I've done processes where I've knocked all the parts off with a an air chisel basically, and then just sanded it down with like a die grinder by hand, and that's fine enough to reuse the plate. Eventually, if you get a lot of nicks and scratches and stuff during part removal, you'll probably want to machine a very small amount of material off the build plate and then rebuild it. And then build on top of it. We say the plates are good for, I don't know, about 50 builds before you need to replace it and get another one. But again, it all depends on the technique and processes that you're using. You could potentially get 3 times that amount, 150 builds on a single build plate before you really need a new one. Something. No.
And it comes with 3. Each system comes with 3 build plates already.
Okay, that's good to know. Yeah, I mean, I know one of our guys, Jesse, asked a question specifically around post processing. So if it's and also with the vacuum furnace for titanium, we remove oxidation in terms of why we would want to go towards vacuum, but also vacuum just tends to make the whole annealing process faster. Is that correct? Like
I wonder. Honestly, that's a good question. I'm not completely certain because once you're in vacuum, you're not getting that conduction from the gas. But now you have your microwave type heating. So in some ways, yes, it could be faster. In some ways, not necessarily. Like a convection oven would be faster, for annealing. So, yeah, it just depends on.
Yeah, the only thing I was just going to mention, Mike, because you said this just a minute ago too, which plays into some of the ancillary equipment too. So if you are dealing with titanium, then we want to talk about utilizing argon as a gas to support that process. If you're talking about other materials, then we're talking about nitrogen. So there is a nitrogen generator also available, but depending on whether you're playing with, like I said, titanium or something else, it's going to be argon or it's going to be nitrogen.
And the nitrogen, you have a generator, and there's an extra footprint, obviously, so it depends on the lab. The argon is more expensive at the end of the day. That's the only reason. Like otherwise, you would just do argon, right? Because it's faster to fill the chamber from a compressed tank, I would imagine, than from a nitrogen generator.
That would be correct, and you can also, fill it from a nitrogen tank if you wanted. But you are 100% correct. The cost of argon tends to be about 3 times the cost of nitrogen.
Right. But the generator that you have, like, kind of, is that mostly what people end up doing, or in your experience so far, what?
I would say yes. Most people do go with the generator, especially if they're not doing titanium.
Sure.
Basically, all the other materials can be done with nitrogen, and it's simpler. Once you have the generator, like you said, sure, the gas down might take a little bit longer, but you don't have to go out and refill it. You don't have to worry about running out. It's going to cost less over time. So yes, even ourselves, we tend to use a nitrogen generator for the majority of our printing.
Right. And so, yeah, I think that before we get into materials, if we just want to take it like where we do walk someone through what it is to print something in Cobalt Chromium. So let's say that they were doing frameworks, RP frameworks in Cobalt-Chrome. What would be the full sort of like workflow for them?
Yeah, that sounds great. Yep, I was going to say, yeah, let's go to this slide, and yep, I will be happy to walk you through that. So honestly, I would like to say overall, it's people are pretty surprised. It's a pretty simple workflow. It's one that they can learn pretty fast. So I've broken it down into a lot of steps here. But overall, you have three main steps. So you have your prepare. So that is where you're scanning and preparing the digital CAD file for production, and then finally nesting on the plate for when you print. And I find that this is something that because a lot of this intraoral scan has become very commonplace. A lot of places are used to CAD, and if you're familiar with that, then the rest of this workflow is actually very easy to learn and very familiar. I think most people would see. The next step after prepare is print, and that's simply when you upload your file to the printer, and the printer does what it does best. So it's laying layers of powder and using the laser to select melt the areas that you want, and it repeats until it's done. And then the final step is the finish process. And so as I had mentioned, you pull your parts out, you want to depowder it. So that could be vacuuming or putting it in a chamber and blasting it with air. Heat treatment. So you just take that build plate, pop it in your heat treatment oven, anneal it so you get your full mechanical properties. Then finally, you're removing your supports. A lot of times that's simple as just by hand. You can use a pair of pliers and pull them off. I think that's another area where people are surprised because they might be used to maybe like plastic or polymers, and they're used to removing those supports. And so they worry if they're dealing with metal supports, it's going to be much harder than the plastic ones. But in reality, that's not true. The connection point to the part itself is usually fairly weak, so you can just pull it off by simple hand tools. And then finally, you'll do your final polish or surface prep or something like that. So as you had mentioned, you might need a little bit of machining or something. Most likely not. Most of the time, either the polish with like a hand tool or even a media blast or something is enough. And then you have your final part that's ready for delivery.
Nice. Do you guys sell a plasma polisher or no?
What was that?
Do you guys sell a plasma polisher?
That one I cannot. Yeah.
I don't think we do.
Yeah.
I think that for a lot of labs, they're going to want that, or in the dental space for the finish that they want and to reduce the labor.
Yeah.
The plasma polisher seems really ideal.
Yeah.
Nice.
Do you guys have some polishing equipment that you sell through your distribution?
Yeah, we have a plasma polisher that we sell.
There you
I
go.
forget the name right now. It's EC. It's the most common one
Okay.
at our site right now.
No, honestly, that's kind of interesting. That's one I haven't actually experienced or seen myself, but I would like to give that a try and see what the results that it returns are there. So
yeah. Like I think that some of the conversations we had around that is like when you need to get rid of the not solvent, but the liquid that you're putting it into, that's a bit of an issue when it comes to like just removal of that stuff for the lab to get rid of that stuff. So it's definitely a concern. But overall, like the plasma polishing tends to make like I said, the uniformity of the part in the finish and also the speed that you can polish it is really fast. Yeah. I'll find the details on the name of it and everything.
Yeah, that'd be great. You want to jump back to the materials for
yeah. So yeah, I figured, now that we've learned a bit about our machines, I would say that's half of the equation. The other half is the material or what you're going to be printing with. So in the dental industry, there tend to be two primary materials. First one I'll talk about is Cobalt-Chrome. A lot of times this is referred to as the workhorse of the dental industry. The reasons for that are it has a really high strength. So there's 1400 megapascal. If you're familiar with mechanical properties, like that's a lot. That's double steel or something like that. It's more than titanium. Titanium is quite strong. It has a high elastic modulus, which means it's quite stiff material, which can be really good for various different implants. And then outstanding wear resistance and corrosion resistance, which, as you can imagine, with dental implants, where you're got a lot of grinding and forces being subjected to it, those are very important considerations. So common applications you'll see for that are these removable partial denture frameworks, so the RPD. And that's, as I stated, its high stiffness is really ideal for that. So you can make a much thinner implant. So it's not as bulky as, let's say, if it was a polymer type production for this. It's kind of fun with this implant that's being shown here. As you can see, a lot of light weighting has been added to it. So there's a lot of lattice structure inside there, those thin lines. So that removes the material overall. It'll reduce the print time. It makes the part a little bit lighter, and it's something that couldn't really be done through traditional manufacturing. You couldn't really mill that or cast it. It wouldn't turn out very well. So those are some of the added benefits that you get from the metal additive or the laser powder bed printing. Then the other material that is commonly used is titanium alloy. It's known as TI64. And the thought behind that is it's more lightweight and tends to be used where comfort for patients is important. It's a little bit more flexible and lightweight, so it's would be less noticeable than a Cobalt-Chrome insert. However, overall, it's got a very high tensile strength, excellent biocompatibility, and corrosion resistance. And yeah, so where you would typically see its use would be orthodontic components, which I'm kind of showing some little brackets there that would be attached to teeth. Surgical guide is another good use, and it can be used in both implants and crowns. It just depends on the patient and what they're going for, if they wanted a Cobalt-Chrome one or a titanium one.
Nice. I mean, like, yeah, there's, from a biocompatibility, I think that's one of the major reasons why people move towards titanium, right?
Yeah, correct. Yep.
Any special considerations if you're welding to either type of these materials, either laser or traditional?
I would say there's not too much of a worry as far as welding goes, especially because of this. The 3D metal printing thing is essentially a micro weld process. So we often say as long as the material is weldable, it's printable. So yeah, so these are both very easily weldable materials.
Okay.
So printing frameworks using a laser welder should be easy, or whatever. It's very much part of the workflow.
Yep. Yep. And then I guess just to reiterate or kind of give a summary of this, it's important to remember that there's no one material here is better than the other. It's about choosing the right material for the clinical application.
Sure. Can we talk a little bit more about, in terms of the materials, the quality difference in terms of like the particle size as well as particle uniformity, and how have you seen that shifting and changing in the recent, or since the time you've been in metal 3D printing?
Yeah, definitely. That's something I can talk about. I can say as far as the material quality and particle size goes, that seems to be pretty industry set and standard. There's reasons for that. When spreading the powder, we have like a recoater. So it's something that essentially, when it lays a layer out, you have a feed system that's moving up, and then a recoater that pushes it over and spreads a thin layer. And so in order for material to be spreadable, there's typical sizes that are used. So it's typically from 15 to 53 micron particle size. So it's something you wouldn't have to worry about. That's just ordered. And so that tends to be what the size is for both of these materials. However, I can say for my time in the industry, the one thing that I have noticed is the price has come down. So there is a lot of powder producers out there, and they're starting to come up with especially new ways of producing the powder. The traditional way, what people used to always do, was what was called gas atomization. So you would just heat up the material to a liquid, spray it through a nozzle, let it air cool, and then filter out the like sand particle you want. And it's nice. You get a very round particle as a result, which helps with that spreadability, as I talked about. It just can be a little bit more expensive. I've seen people starting to do more what's called mechanical production. So maybe high energy milling, or a lot of them, I got to be honest, I keep having a lot of people come up to me and tell me they have new techniques, but it's all proprietary. So they're unwilling to explain what they're doing and how they're doing it. They're willing to show their PDS, or the particle size distribution, and the mechanical properties and chemical analysis, and everything is what you need. But the benefit is they're producing it much less expensive. And so that's what I've seen. I've seen the price of titanium powder almost cut in half. It was originally pushing about $300 per kilogram, which is fairly expensive. Nowadays, I'm seeing it go for about $150 per kilogram. So that's a great reduction there. And Cobalt-Chrome was always a little less expensive, but it's also dropped in price too. So that's been kind of the things that I've been seeing. And then there's
particle size distribution. Can you tell us? Sorry, I didn't mean to.
Oh yeah, no, go ahead. Yep.
That part, like, so is that where we're trying to, like, get, if we're, let's say that we have this powder and it's all 15 micron, it's per, you know what I mean? Would that make a huge difference for finish quality for the print, or?
Yes, for certain. Yep. And I would say so the sweet spot, as I said, was that like 15 to 53 micron size. And then, as I talked about, you have a sieving unit, which usually has something like a 73 micron size. So you're getting some particles that are bigger. There are people that sell what they call coarse powder, which is a much larger particle size. So that's going to be less expensive, but it's not going to spread as well. And if you get too big of a particle, as you said, or as we showed, we have a layer size from that 20 micron to 50 micron, something like that. However, if you have too big of particles, it's not gonna spread those thin layers very well. So that's something that can be an issue. Now, the other side of that is very fine powder. If you can get more fine powder, you really do get a better surface finish. You're going to get better energy absorption of the laser in general, and you're going to get better packing when you relayer it. So you do get a better surface finish. Now, the only downfall to that is very fine powder is not as spreadable. It becomes more densely packed and harder to push, so it doesn't like to spread. So that's the reason why there tends to be that 15 to 53 that you see that most people use, and typically round powders. But I have seen fine powder used. I've been very impressed with the finishes you can get. And I've seen irregular particle shapes, meaning not spherical, like ovals and really bizarre ones. And sometimes the way that's manufactured, it spreads just fine. So it's one of those things that you can test and find out, and you can get some really good results from that too. It can be less expensive to produce, and you can get higher packing density and better results. But that was one of the things that I was actually going to bring up. That's really nice about our company and our system is we're very open source. So we have powders that we've identified, that we've developed parameters to, that we sell and use. However, you are not stuck to that. You are free to use any powder that you want, another supplier, and that's something that we can help with. And we're more than happy to help develop the parameters and process. And it's the same thing with software. You're not stuck with one proprietary software from us or some company. You are open to use whichever software you would like. So you're free to develop, I guess, your own kind of workflows there, which is, I would say, one of the main advantages of going with our company and working with us. A lot of our competitors, you are stuck with their powder, their pricing, their parameters, and their software. And there are costs associated with all those things.
Sure. Sure.
All right, I know we're time sensitive with 4 minutes to go, so just want to make sure if there's any questions or comments or any other direction you want to take this, Mike. Want to make sure this is still valuable information to share.
Absolutely.
I just want everyone to know that the systems are available through 3DNA Dental, and we're happy to have a relationship with you guys. You're very knowledgeable, and like you said, if we want to go ahead and open it up to any questions, and we do have some specials for anyone who's attended this today. So
yeah, I mean, I think we don't have any questions in the list right now, but I think that one of the questions I would have is just like, what have you guys seen as in the dental space specifically as the most, just with the clients you've worked with so far, what's in the highest demand in terms of, for a lab, this is what we want to print with this, you know what I mean? Like,
yeah.
Again, for us, we try to convince or encourage our clients to specifically choose a target and nail it, do that first and then do the next one, like really, so that you can add value and not turn it into like an experiment, you know what I mean? So
Yeah, I'll answer that, and then if George has some thoughts on that as well. I'd say that the biggest impact tends to come from cases where fit, repeatability, turnaround, production volume matter. So dental coppings, crowns, bridges. He mentioned earlier the RPD frameworks, implant supported frameworks, Cobalt-Chrome applications are all strong examples. Financially, the biggest wins often come from parts that are being outsourced today. So that's probably a place to look first. All parts that require a lot of manual labor through the traditional casting process. So clinically, the value is consistency. So you're moving from multi-step manual process to a digital workflow where design, nesting, print parameters, post-processing can be controlled. And that impact is both financial as well as clinical. So that's my thought. And then, like I said earlier, people usually find one application or maybe two that they go, I think this is a place where we can save some bucks and have a better output. And then all of a sudden it turns into a third or fourth or fifth application where they could get a return on investment as well.
Right.
George, any thoughts from what you're seeing?
Yeah, no, I was going to say that was pretty much what I was going to say. Just to add a little bit more information, I would say that especially that fit, like you said, that's where you see one of the greatest benefits of this. And for instance, traditional casting, let's say you were making one of those RPD frameworks or something like that, has a tolerance of about 130 microns versus, as we stated, ours is about 25. And so that slight difference can be enough to make it so the fit isn't very comfortable and very good, and then you'd need to do another iteration in order to get a implant that's perfect. So ours off the top or off the bat is already better tolerance, so you're going to get a better fit. And then if you did happen to actually need to, the turnaround would be a lot faster.
Yeah, good question.
But I like that. I think you're absolutely right. Like whatever you're outsourcing right now, that's the easiest way to understand where you're going to immediately save money. And then the question is, what do you want to target? What are people asking you for?
Mm-hmm.
Awesome. Well, guys, I really appreciate your time. I think we learned a lot about Mastrex and more about laser powder bed fusion and what the steps are to really accomplish that in-house. So anybody listening and watching this later, please reach out with any questions and to learn more. And yeah, just really excited to bring this technology to more hands.
Absolutely. No, we appreciate the time with you and appreciate the time with the audience and the questions. And I'm sure these questions beget other questions, but Paul and Mike are the guys to reach out to, and we're here to support in any way we can to see if this would work for your particular lab and your particular scenario, your particular application, and make a good decision for your business. So that's what we're here to do to help.
And where 3DNA can really help too is sort of complete the package, where it's like, having a metal 3D printer is one thing, but you guys, as you well know, like what George was talking about, is like the design side and being able to go from A to Z is such a huge number of things that no one company really covers the whole thing. So that's where we try to help and connect all those dots for everybody. So.
Excellent.
All right on, guys. Well, we appreciate your time, and we will hopefully do this again not too long from now, and be putting a bunch of setups in a lot of people's labs and learn so much together.
That sounds great.
Yep.
Right,
Sounds
okay.
great.
Thank you.
Thank you, everybody.
Aloha.
Sure.
All right.
Bye.